So up to last class, we have started diffraction. Diffraction is the phenomenon of bending of light. We were doing single slit diffraction, that this is source. This is single slit and this is screen. The diffraction that we are discussing is Fraunhofer diffraction. So source and screen are at infinite separation. So we place the lens here so that the rays coming from the source becomes so the rays coming from the source becomes parallel after diffraction. So there are various things. These rays can move without any deviation or they can bend at some angle. So to converge these light waves over the screen, we need a lens. So I placed a lens here. Okay, so to converge these waves on the screen, we need स्क्रीन पर अगर आपको इन वेव्स को कन्वर्ज करना है तो कन्वर्ज करने के लिए हमने कॉन्वेक्स लेंस यूज किया था. तो ये सारी कहानी हम कल डिस्कस कर चुके थे कि यहाँ ये कन्वर्ज हो जाएगा. So to converge these waves on the screen, we are using this convex lens. This convex lens will converge these waves on the screen and you will get fringes here. The fringe here is known as the central maxima. Similarly, convex lens will converge. Convex lens will converge here. These waves here. Will converge these waves here. So this point P is some nth fringe. Some fringe, some random fringe. It could be maxima or minima. We have discussed the path difference between waves reaching point P from A and P. We have dropped a normal from here. We call this angle as theta n. This is n. This is the path difference, and this path difference comes out to be, what was the value of this path difference?
A sine theta n.
Yeah, that path difference was A sine theta n. So this is path difference, okay. So this was the path difference that we did yesterday. So I'm summarizing everything. This is point P. The waves are reaching point P from A as well as B. The waves reaching point P from A and B have a path difference which is A sine theta. Now, depending upon the path difference, you can get a minima or a maxima. So you can get a minima or a maxima. So let's study. We did one more thing. This theta n was angular separation. We have also discussed that the separation between this slit and screen is capital D. We have also defined this linear separation. We defined this linear separation into two ways, that tan theta n is yn by d. That's first way. Or using small angle approximation, we have defined that this yn is theta n multiplied by d. That is equation number 3. So we have derived all these three things in the previous class. Now, today we just have to discuss the conditions for this path difference for which the fringe at point P is a maxima and the condition of path difference for which the fringe at point P is minimum. That's it. And the best thing is, unlike interference, you need not derive anything. In interference, we have derived the condition of maxima and minima. But in diffraction, you need not derive anything. You just need direct results. Just memorize those results and solve the variables. Derivations are not a part of your syllabus, not a part of school syllabus. So I'm not deriving any result. So first I'm writing condition for nth secondary minimum. Condition of nth secondary minimum. So the condition of nth secondary minima is your path difference. I should write as path difference. Your path difference should be equal to n lambda. Or you can say that path difference, which is a sine theta n, is equal to n lambda. This is the condition of secondary minimum. Your path difference is n lambda. This theta n is angular separation. So from here, if you want, you can write your sine theta n is n lambda by a. Here, lambda is the wavelength of light. N is the number of fringe. For first minima, n is 1. For second minima, n is 1. N is 2 for second maxima, and so on. And a is the slit width. This width of the slit is a. So sine theta n is n lambda. If I use small angle approximation, then I can write this sine theta n is almost equal to theta n, which is equal to n lambda by a. If angle is small, then I can use this approximation. Next thing. For linear separation, if you want linear separation, right? You can use this thing that linear separation yn is angular separation multiplied by d. This is the linear separation. So you can write that your linear separation is angular separation, which is n lambda over a multiplied by d. But again, this is valid only if you have small angle approximation. Otherwise, you have to use small angle approximation. So use this when small angle approximation is valid. If a small angle approximation is not valid, if small angle approximation is not valid. If it is not valid, then use this expression that tan theta n is yn by d for linear separation. But in majority of cases, small angle approximation would be valid, so we'll use this relation simply that yn is theta n into theta. So that was the condition for secondary minimum. Let's do one more thing. So you need not derive this expression that why the condition of secondary minima is n lambda. I'm not deriving it. But yes, through some logical arguments, I will prove why n lambda corresponds to minimum. But again, that will not be the derivation. That will be just a logical proof that why n lambda results in a minimum. After minima, let's do one more thing. Condition of nth secondary maximum. Condition of nth secondary maximum. Nth secondary maximum. For nth secondary maxima, you can use this equation that path difference is 2n plus 1 lambda by 2. And remember that your n starts from 1 here. And will start from 1. So what is path difference? Path difference is a sine theta n. So your a sine theta n is 2n plus 1 lambda by 2. So you can write that sine theta n is 2n plus 1 lambda over 2a. That is sine theta. This is sine theta. Again, you can use small angle approximation if you use small angle approximation. If I use small angle approximation, then I can write that this sine theta n is almost equal to theta n, which is equal to 2n plus 1 lambda by 2a. This is small angle approximation. 2n plus 1 lambda by 2a. Similarly, you can write yn, linear separation. So you know if small angle approximation is valid, if small angle approximation is valid, then you can write that yours yn is theta n multiplied by d. So for theta n, you can substitute from here. So your yn will comes out to be, it's 2n plus 1, it's lambda divided by 2a multiplied by d. That's why. So this is your y, separation of nth fringe from the center right fringe, 2n plus 1 lambda d by 2. Okay, now solve this numerical. It's a simple formula based numerical. So in the first part, angular separation is it's n lambda over a. So I need a first minima, right? So first minima is theta 1. So that's lambda by a. Lambda is 6,000 angstrom. So that's 6,000 into 10 raised to the power minus 10 divided by a. A is 2 mm. So that's 2 into 10 raised to the power minus 3. So your theta 1 is 3 into 10 raised to the power minus 10 plus 3, it's minus 7. It's minus 4. Next, you can calculate the linear separation, that is theta 1 multiplied by d. So you can write that your y1 is theta 1, which is 3 into 10 raised to the power minus 4 into d, which is 2. So y1 comes out to be 6 into 10 raised to the power minus 4. So that is for the first part. For the second part, you can use that your theta n is, it's 2n plus 1, it's lambda by 2a. So if I substitute values, theta 2, I need separation of second secondary maxima. Then it's 2 into 2 plus 1, it's lambda over 2a. So your theta 2 is basically, it's 4 plus 1, 5. Okay, 5 lambda by 2. This is 5 lambda over 2a. So if I substitute values here, it's 5 into lambda, which is 6,000 into 10 raised to the power minus 10 by 2 into a, which is 2 into 10 raised to the power minus 3. So yours theta 2 is, it's, if I cancel this here, this is 3,000. 5 3s are 15, it's 7.5 into 10 raised to the power minus 7 minus 4 radian. For linear separation, just multiply it with d. So y2 is 7.5 into 10 raised to the power minus 4 multiplied by 2 meter. So that comes out to be 15 into 10 raised to the power minus 4. Okay, solve it. Next question. So 600 nanometer is the wavelength. So lambda is 600 into 10 raised to the power minus 9 meter. The resulting diffraction pattern is obtained on a screen 1.2 meter away. So the capital D here is 1.2 meter. It is observed that first minimum is at a distance of 3 mm. Means your Y1 is 3 mm, which is 3 into 10 raised to the power minus 3 meter. You need slit width. So for the first minimum, the separation is this lambda d by a, the linear separation of first minimum. See, the linear separation of minima is n lambda d by a. This is first minima. So it's lambda d by a, right? You need a. So your a is it's lambda d divided by y. So if I substitute values, your lambda is 600 into 10 raised power minus 9. Your capital D is 1.2. Y1 is this 3 into 10 raised to the power minus 3. So this 3 will cancel this thing, it's 200. So your A is 1.2 into 2 is 2.4 into 10 raised power minus 7 or minus 4. So that's 2.4 into 10 raised power minus 4 meter. See, this is the formula, right? This is the formula. 2n plus 1 lambda d by 2l is the formula for central maximum. So your yn is 2n plus 1 lambda d divided by 2. Okay, let's check which one of you is correct. This is for the second order maximum, means just put n equal to 2. When you put n equal to 2, that's y2, which is 2 into 2 plus 1. It's lambda d divided by 2a. So your y2 is 5 lambda d over 2a. You need a. So your a will be 5 lambda d divided by twice of y. So it's 5. How much is lambda? Where is lambda? This is lambda. 5 into 600 into 10 raised to the power minus 9. Nano is minus 9. 2 into y2. And multiplied by yes capital D, which is 0.8. Y2 is this 15 into 10 raised to the power minus 3. So if I cancel, then this 5, 3, 3, 200. And I cancel it with this, so this is 100. So your A comes out to be 0.8 into 10 raised to the power minus 7 meter. The next is that's the width of central maximum. See, in interference, we have calculated width of all bright fringes and all dark fringes. We got that width of all fringes was same, which was lambda d by d. But this is not the case with diffraction. We have seen an experiment yesterday that in diffraction, the width of central maximum is maximum, and then of the next maxima, it keeps on decreasing. For the central maxima, the width is maximum. Then on the next maxima, this width keep on decreasing. So in diffraction, we don't really calculate the width of each maxima. What we calculate is just that of central maximum. So I'm drawing the pattern. This is the single slit. This is the single slit. And this is the screen. Single slit, and this is the screen. So this is central maximum. This is the central maximum. The fringe next to central maxima is first minima that we have seen yesterday in the experiment. That just after central maxima we have minima, that's first minima. So if you want to calculate the width of central maxima, the easiest thing is calculate the separation of first minima from the central maxima, this separation, and double it. So I can say that width of central maxima is the separation between two first order minima on both sides of central maximum. On both sides of central maximum. So if you can calculate this separation, the separation of both the minima, first minima to first minima, this separation, then this separation is exactly equal to the width of central maximum. And you can calculate both types of width, like the linear width as well as the angular width. So simply I can write that angular width of central maximum, angular width of central maxima is equal to, say this is the first one, this is the second angular separation. This is it. So angular width of central maximum is twice of theta 1. That means the angular separation of first minima, both the first minima. This theta 1 plus theta 1 is the angular width of central maximum. You know that theta 1 is lambda by a. So this is the width of central maxima, 2 lambda by a. So once you have the width of central maxima, you can also calculate the linear width. That was the angular width. Now you can also have the linear width of central maxima. So for linear width, we always multiply angular width with d. So we just write this as, this is angular width multiplied by d. Angular width is 2 lambda by a multiplied by d. That is the linear width. So the linear width of central maxima is twice of angular width, 2 times lambda d by a. So this is how we calculate the angular width of central maxima, and this is how we calculate the linear width of central maxima. Estimate So I don't think that you will need wavelength of light in this numerical. This numerical basically says that you have a single slit experiment, means single slit diffraction, and this is the maxima of single slit diffraction. In the maxima of single slit diffraction, asking some bright fringes of interference fringe. This is for diffraction, and this is of interference. So he's simply asking that how many bright fringes of interference will fit into one dark fringe of diffraction. That is the question. This is the simple question. How many bright fringes of interference will fit into the central maxima of diffraction? So to solve this, you can start from this way. Let n bright fringes of Young's double slit experiment, which is interference, fits into center maxima. Central maxima of diffraction. So if n bright fringes fit into the maxima of diffraction, that means n into fringe width, n into fringe width of bright fringe is equal to width of central maxima. This is equal to the fringe width of central maxima. Fringe width of bright fringe is simply it's lambda d by d in diffraction. Width of central bright fringe is lambda. This we have calculated in last section. 2 lambda d by a. So it's lambda d by a multiplied by 2. So see, this lambda will cancel this lambda. D will cancel this lambda. Your n is simply it's 2 by a into d. Now there is one small correction here. Okay, some data is missing. That was what I was thinking. Fringe width nahi, that is slit width. Or for diffraction, A is given as 2m. A is 2m. So what you can do is, no, it's not 2 mm. Just let me check the question. What's the value of A? A is 0.2 mm. It's 0.2 mm. So you just have to calculate how many fit bright fringes fit. So that's 2 into D, which is 0.5 mm, divided by A, which is 0.2 mm. You can convert 0.5 into meter by multiplying with 10 raised per minus 3. You can also here multiply with 10 raised per minus 3. But these multiplication factor will cancel out each other. So your n will comes out to be 5. So you can say that 5 maxima of interference will fit into the central maxima of diffraction. This is an important question. This was in CBSE exams 2017. After this numerical, the next is intensity distribution curve. Intensity distribution curve. So I basically need a graph which represents intensity and part difference. So for maxima, not for first, let's say for minima, part difference is n lambda. Yes, it's right. So for first minima, your part difference, put n equal to 1 is lambda, 1 into lambda. For second minima, your part difference will comes out to be it's 2 into lambda and so on, 3 lambda, 4 lambda, 5 lambda, that is from minimum. For maxima, part difference is 2n plus 1 lambda by 2. This is part difference for maxima. For first maxima, the part difference is, put n equal to 1 here. So that's 2 into 1 plus 1 into lambda by 2. So that is 3 lambda by 2. Similarly, you can do it for second maxima. For second maxima, the path difference is 2 into 2 plus 1 into lambda by 2. So that's 4 plus 1, 5. It's 5 lambda by 2. This is the part difference for second maximum, and so on. So now, if I plot a graph between intensity and the part difference. So when part difference is 0, it's central maximum. When part difference is lambda, you have minima. When part difference is minus lambda, you have minima. After lambda, it's 3 lambda by 2. When your part difference is 3 lambda by 2, you have maxima. When part difference is minus 3 lambda by 2, means there are minima on the above the central maxima and below the central maxima. So this right hand side means above the central maxima, this is below the central maxima. Similarly, you can write other values as well. Like after 3 lambda by 2, you can write 2 lambda, it's 2 lambda, which is minimum. Then you have 5 lambda by 2. And then you have here also minus 5 lambda by 2. This is again minimum. So this is it. This is central maxima. This is first minima. This is central maxima. This is next minima. This is central maxima. Similarly here, central maxima, minima, this is central maxima, minima, then again central maxima, and then there would be minima. So if you can see from the graph that central maxima, the intensity is maximum. Their intensity of next maxima is just exactly 1 by 21 of the central maxima. Then this is 1 by 61 of the intensity of central maxima. Similarly here, 1 by 21 and 1 by 61. Where I here is intensity of central maxima. So intensity of central maxima. So in interference, the intensity of all maxima is same. When we have draw this graph in interference, the graph was like all have same intensities. But in diffraction, the intensity of central maxima is maximum, then it keeps on decreasing, which is very clear from the graph. So this is intensity distribution graph for diffraction. After this, you can get a question on writing differences between interference and diffraction. Difference between interference and diffraction. Just comparison of interference and diffraction. So the first difference. The interference is due to superposition of light waves from two coherent sources. Interference is due to superposition of waves, of light waves from two coherent sources. So if you have two coherent sources, then light waves coming from these two coherent sources will superimpose to give interference. While in diffraction, you don't have two different waves. It's basically the different wavelets from the same wave will superimpose. So this is superposition. This is superposition of secondary wavelets from same wavefront. So that is the first difference. The second difference is in interference, all bright fringes are equally bright. But in diffraction, the intensity of all bright fringes is not same, it decreases. So here, all bright fringes, you can also call them as maxima, have same intensity. But in diffraction, this intensity is not same. This intensity decreases. Intensity of maxima decreases. Intensity of central maxima is maximum. Intensity of central maxima is maximum. Third one. The third difference is width. All fringes have same width. All fringes have same width. Means all bright fringes, all dark fringes have same width. But here fringes have different width. May have different width. May have different width. Width of central maxima. Width of central maxima is maximum. Then this width decreases. The width of central maxima is maximum, then it decreases. The next is in interference, there is a very good contrast between dark and bright fringes. The intensity of dark fringe is very low. The intensity of bright fringe is very high. So there is a very good contrast between the bright and dark fringes. But in diffraction, there is no such good contrast. So a good contrast between bright and dark fringe. So contrast here between maxima and minima is poor. The contrast is not good. The contrast is poor. The poor contrast between maxima and minima. So these are the major differences between interference and diffraction. If I draw two waves in this wave, this is one wave and this is another. And I say that these two waves are superimposing. Just by looking at the diagram, can you tell me what type of superposition would be this? This would be constructive or destructive? Destructive, not constructive. It's destructive superposition. See, the crust of one wave will fall on the trough of another. So these two waves will get subtracted. So this is an example of destructive superposition. This is an example of destructive superposition. Crust of one wave will fall on the trough of another. This is destructive, not the constructive superposition. So by looking at the diagram, you can decide whether the waves will add up or they will cancel out each other. If they have same amplitude, then they will add up in cancelling each other. These two waves will simply cancel out each other. This is an example of destructive superposition. But you have to decide these type of superpositions from part difference. If part difference between two waves is lambda by 2, then they will have this type of geometry. If part difference is lambda by 2, that means they have this type of geometry. The part difference of lambda by 2 will result in destructive superposition. Wave will cancel in each other another if part difference is lambda by 2. Just note it down. If part difference is lambda by 2, then superposition is destructive. Superposition is destructive. This is an example of destructive superposition. The next is after this constructive and destructive superposition, the next thing is Okay, do this question. So if the waves coming from the 2 points are having a path difference of lambda by 2, then it's very clear that they will superimpose destructively and they may cancel out each other. So this is the slit of width A. I'm dividing this slit into two equal parts. This is A by 2 and this is A. Part difference is lambda. That means part difference between waves coming from point A and B is lambda. Part difference between waves coming from point A and B is lambda. So the part difference between waves which are coming from point A and B is lambda. Now, if I divide this slit into two equal parts, I'm dividing this slit into two equal parts. Dividing slit into two equal parts. I'm dividing this slit into two equal parts. The part difference between waves from the upper part and the lower part of this slit will be lambda by 2. So if I'm dividing the slit into two parts, that means I'm dividing the part difference into two parts. So part difference between waves coming from upper and lower half part, lower half portion have part difference of lambda by 2. So the part difference between waves which are coming from the upper part and the lower part have a part difference of lambda by 2. Now, if they have part difference of lambda by 2, we have already seen that they will superimpose destructively. So waves will superimpose destructively, resulting in minimum. So this is the explanation why a part difference of lambda results in a minimum. If in the question instead of lambda, 2 lambda is given, then remember you will divide this slit into 4 equal parts so that part difference between any two parts is lambda by 2. And divide it into 4 equal parts, lambda by 2, lambda by 2, lambda by 2, lambda by 2. So you have to divide the slits into number of parts so that the part difference from any two parts is lambda by 2. The next question is why part difference of 3 lambda by 2 results in maximum. So this is the slit. The waves coming from point A and point B will have part difference of 3 lambda by 2. Waves coming from A and B will have path difference of 3 lambda by 2. So the waves which are coming from A and B will have a part difference of 3 lambda by 2. Now you can divide this, the slit width is A. You can divide this slit into 3 equal parts. You can divide this into 3 equal parts, A by 3, A by 3, A by 3. You can divide it into 3 equal parts. So the waves, so you are dividing basically this part difference of 3 lambda by 2 into 3 equal parts of lambda by 2 each. So we divide slit into 3 equal parts. So the waves coming from the first two paths will have a phase part difference of lambda by 2. Waves coming from first two parts will have part difference of lambda by 2. So they superimpose destructively. So they will superimpose destructively. But wave from the third part, however, wave from third part will contribute to maximum, to sets maximum. The waves from the first two parts will cancel out each other, but the wave from the third part will survive. That will result in maximum, and that wave will contribute to maximum. So next, this is the next theoretical question on diffraction.